Hello everyone, welcome to the RCNP course. In this part, we're going to introduce the track RNS principle. And firstly, let's take a view of the principle of track RNS. A track traces the returned result of an object to change the status of itself. Then the associated function model, such as static routing, such as VRP, takes a corresponding action based on the track status change. After the local device sends an RCNP echo packet, the peer device responds to the RCNP reply packet. RNS, which stands for Ruijie Network Services, detects whether the peer response packet is received to monitor end-to-end connectivity and network quality. A track is generally used together with RNS. A track sets the status of itself to up or down based on the RNS detection results. And as you can see here are the steps. The first step, RNS uses RCNP equal detection to test the connectivity of the ISP's network. And then a track calls an RNS and set the status of itself to up or down based on the RNS detection results. Is displayed or removed in the routing table based on whether the track status is up or down. So we can tear it into two parts, track and RNS. About the track, let's take an overview. RCNP equal detection is the most basic function of RNS. Is compliance with RFC 2925. The principle is that RCNP packets are sent to determine the reachability of the destination and calculate the network response time, packet loss rates. Based on the config detection time and frequency, RCNP equal detection sends RCNP equal request packets to the destination IP. Then, based on the receiving time and number of RCNP equal response packets, RCNP equal detection calculates the response time and the packet loss rates to the destination IP, reflecting the current network performance and conditions. The results and the historials of RCNP equal detection are recorded. And you can run a command to display these records. RCNP equal detection succeeds if the destination device can correctly respond to RCNP equal request packets. You can see the package between them. The sender will send the RCNP equal packet to the reception, and the reception will reply to this request. So from here, you can find actually the working principle is quite easy to understand. So next, let's see the configuration of it. To configure RNS, the command is shown here, IP RNS1. By using this command, we created the RNS1. And then RCNP equal 12.12.12.1 out interface, next hop, source IP. So here are three parameters that we should specify during the configuration. Okay, in the next timeout 5,000. 5,000 means 5 seconds, right? Because 5,000 is 5,000 microseconds. Frequency 5 seconds. So it represents that we will set the detection timeout period to 5 seconds. If no detection response is received in this period, detection fails. Frequency 5,000 means that we send the detection every 5 seconds. So 5 seconds is the interval of the detection packet. And then after finishing the configuration of RNS, next is the configuration of track. Track 10, RNS1. 10 actually is the ID of this track session. RNS1 means the RNS we just created, because when we create the RNS, ID is 1. And delay down 5, up 5 means the track to down or up 5 seconds after the RNS detection fails or after the RNS detection succeeds. Okay. So after knowing the configuration, next let's see the application of it. The typical application of track here is association with static routes. Let's see the background. A router of a bank outlet, router A, interconnects with router B and C of the provincial branch through ISP and MSTP private lines. Router A accesses the 192.168.10.0 network segment of the provincial branch intranet through a static route. The line from router A to router B is an active link. And obviously, the line from router A to router C is a standby link. For service reliability, when the link from router A to router B fails, services needs to actively switch to the backup link. So here what we use track is to monitor the running status of these two links and switch the traffic between these two links when the network is faulty. Okay, so let's see the configuration in this scenario. Firstly is to configure RNS, IP RNS1, RCNP equal 9.9.12.2 is a detection destination address. Timeout 3000, frequency 3000. So the interval is 3000 or 3 seconds. And track 1, RNS1. So we use track 1 to track the RNS and delay up 5, down 5. So it means that 5 seconds after the detection succeeds or fail, we will change the state of track. And since we are using RNS associating with the static routes, so we should configure the static routes. And which is special here is that this is a float routing, means we have an active link and a backup link. So we should change one of the maybe preference value of these two routes. Let's see the configuration. IP route 192.168.10.0, mask length is 24, of course, mask here. G00, the interface G00, the destination is 9.9.12.2, track 1. We call track 1 in static routes. And for the other is similar, but which different is here. Configure floating static routes by changing the preference value of this entry to be 150. Okay, and after finish the configuration, we should verify the results. So you can see when the active link is normal, after checking the status, you can see here, shoot IP route to the destination 192.168.10.0. You can see it's via 9.9.12.2, and the state of the track here is up. But if we shut down the interface, for example, when the active link is abnormal, by shutting down the interface, and when you check the IP route, you can see it has switched to another path because the interface and you can see the IP address here is different. And when you check or verify the status of track here, the state is done right now. So it means in this case, track has taken effect and has switched the traffic activity to the backup link. Okay, this is an association with static routes. Of course, we can use RNS to associate with other protocols. For example, here is VRP. A customer deploys 2 egress routers connecting to 2 different internet lines of the ISP. The routers are connected with the VSU of the core switch in downlink direction. The data of intranet users is forwarded to an egress router through the core switch to access the internet. And the requirement is obvious. Static routes are configured between the core switch and the egress routers. For intranet user data access to the internet, to the link to router A is active, and the link to router B is a backup. We use VRP to achieve the master and backup rules for these 2 routers. If we want to improve the reliability in this scenario, we can use RNS to track and use RNS to change the status of VRP. So let's see. VRP is configured on the ports of router A, B's downlink to the core switch. Default route of the core switch directs to the VRP virtual address, and a track is configured on router A to detect the status of the uplink to router A. And once the link is faulty, the traffic should be actively switch to the backup link, which is router B. Okay, after knowing the requirements and background, next let's see the configuration. Actually, here are the basic configuration of VRP, right? I think it's really easy for you to understand. Which special is here? VRP1 track 9.9.23.2 60. It means that we detect the connectivity of 9.9.23.2 if the address is unreachable, decrease the priority to 60. Since once we decrease the priority of this device, it will not be the master of VRP anymore, and router B will be the master, and all the traffic will go through router B. Okay, and VRP1 permits delay X, enable the permission delay. This is optional, but if we use the permit delay, we can maybe solve the problem that's caused by the frequent switching between router A and router B in VRP. So it suggests to use this command. And on router B, it's just the basic configuration of VRP. And after finishing the configuration, let's verify the results. When the active link is normal, you use a few VRP brief on both router A and router B, you can find that the master ID here is 9.9.12.1. Actually, it's router A. Right. When the active link is abnormal, you can find router A becomes the backup, and the priority has been decreased by 60 from 150 to 90. Right. And on router B, you can find it has switched from backup to master, and you can see it's a master already, right? Okay, so this is the association with the VRP. So about this part, you can see that a track traces the return result of an object to change the result itself, and the associating function takes the corresponding action based on the track status change. So in this way, we can improve the reliability. Okay, so about this part, let's see a question. What statements are correct about the command VRP10 track fast Ethernet 0, 24, 50? So here there are some parameters inside. Firstly, A, 10 indicates a VRP group. Of course, it's VRP10. So 10 is the net ID of the VRP group, is correct. B, track enables a VRP tracking function. Obviously, it's true. C, 50 indicates that after F024 becomes invalid, VRP priority is reduced to 50. Okay, and the D is reduced by 50. So you can find that 50 represents that once the port is invalid, the VRP priority value is reduced by 50, while not to 50. So here we choose A, B, and D. Okay, that's all for this part.